On the last occasion we had concluded with the circuit of the Winbridge oscillator. Did we analyze the oscillator circuit? We didn't. The circuit is this. In all these circuits we represent the amplifier, the basic amplifier, by means of a block, and usually it is realized in the form of an op amp, by modification of an op amp, but there is no reason why a single transistor or two transistors cannot be used. Okay? And if instead of op amps transistors are used, then obviously there would be imperfections in the input and output impedances, which you will have to take care. So we analyze ideal circuits and we leave non-ideal circuit analysis to you. We have an amplifier, a zero phase amplifier, which is realized by means of an op amp with two resistances, let us say R1 and R2, and the output is this. You know that between this point and this point the gain is 1 plus R1 divided by R2. This is the gain, which means that the gain has a phase shift of 0 degrees, and therefore for oscillations the feedback network or the beta network has to produce 0 phase shift and an attenuation which is 1 by 1 plus R1 by R2, and this is done by means of a simple CR circuit, RC circuit, a series RC and a shunt C and an R. This is the beta network, and it is a voltage feedback. A part of the voltage is connected here. One of the basic philosophies of oscillator analysis is, here of course you can very easily identify the A circuit and the beta circuit. The beta is equal to this voltage divided by this voltage, okay, which is simply R by 1 plus j omega C R. This is the shunt circuit, shunt impedance, divided by R plus 1 over j omega C plus R divided by 1 plus j omega C R. Agree? This is the beta circuit. It is very easy to identify. It may not be so if the input impedance here was not infinity, then you might have to include the input impedance here. Okay? So you will have to take care in oscillator analysis. But nevertheless, one of the basic philosophies in oscillator analysis is that you open the loop. Yes, please. I am not turning it here anyway. Yes, yes. Why I put this RNC? This is to produce oscillations at a specified frequency. That is, the beta network, beta now is a function of omega, and the Barkhausen criterion, which is A beta equal to 1, has to be satisfied at a single frequency. Then only we get sinusoidal oscillation. That selection of frequency is done by this. As I had indicated last time, this circuit RC is a band pass filter which has maximum response at omega 0 equal to 1 by RC. The maximum response occurs at omega 0 equal to 1 by RC, and at the maximum response the phase shift is 0, and therefore this is an appropriate network for selecting the frequency by this oscillator. All right. But what I was mentioning is the following, that in any oscillator circuit the philosophy is the philosophy of analysis. You don't have to identify A and beta. If the circuit is complicated, you don't have to apply feedback method. There is a simpler way. What you do is simply you open the loop. Don't close the loop. Oscillator is a closed loop circuit, positive feedback. What you do is don't close the loop, or if the loop is closed, well, you open it somewhere. But take care that in this opening the beta network faces what it was facing in the closed loop. That is, if the amplifier has a finite input impedance, after opening the loop, put this input impedance here. Is the point clear? That's all that you have to do. Then you analyze the circuit. You analyze the circuit and apply a VI here and find out the condition under which this is also VI. Is the point clear?
So is it not like splitting that short circuit wire into two parts?
No short circuit. I have shown it by a block diagram.
You see that wire joining A and beta circuit.
Yes.
That wire splitting into two ports that goes across A and beta, giving it.
Oh, you see, there is another point which is grounded. The beta network is also grounded. Whatever the connection is from input, from output to input, okay, you break the connection at the amplifier input. You break the loop. Apply a voltage VI at the amplifier input. Obviously, if oscillations have to occur, then the output of the beta network must also be VI, because the total transfer function, which is A beta, should be equal to 1, 0 degree, and therefore you argue that if this voltage is VI, this voltage has also to be VI. This is a simple philosophy of analysis of oscillator circuit. Any oscillator can be analyzed by this, provided you take this care that whatever loading the beta network had in the closed loop must be kept intact. That's all. For example, if this is a transistor, input, let's say this is grounded, then this R pi has to go into the beta network. Is the point clear? That's only care. After that you can do it routinely. There is no problem. You do not have to identify A separately, you do not have to identify beta separately. In an op-amp based circuit it's very easy, because op-amp gives near ideal conditions: infinite input impedance, zero output impedance, only a gain, either a plus sign or a minus sign. But this is not true if you had, instead of an op-amp, an FET stage, for example. An FET stage would have had a high output impedance. High input impedance is okay. On the other hand, if it's a BJT stage, then the output impedance would be high, input impedance would be low, and therefore both have to be taken into consideration. Okay. Now going back to the Winbridge circuit, the A beta is 1 plus R1 divided by R2, and the beta can be simplified to the following: 3 plus j omega CR minus 1 by omega CR. The expression for beta, if you clear this, if you clear off 1 plus j omega CR, and j omega C goes up, so it becomes j omega CR divided by a polynomial, then you divide both the numerator and denominator by j omega CR. This simple algebra, you can show that this is the final story. Beta is 1 by 3 plus this, and this has to be equal to 1. The angle of the right hand side is 0. The angle of the left hand side can be 0 only under the condition that omega CR is equal to 1 by omega CR, and therefore omega 0 is 1 by CR. And under this condition, yes, no under root, omega squared, cis squared, R squared is 1, therefore omega is 1 by CR, and 1 plus R1 by R2 should be equal to 3. If this is 0, then this should be equal to 3, which means that R1 should be equal to twice R2. The feedback resistance has to be twice the input resistance. Okay, these are the simple conditions. Of course, you know that the gain, exact gain of 1 plus R1 by R2 may not start the oscillation. You might have to put a little bit extra. We'll come back to this in a moment. But first, why is it called a Winbridge oscillator? Why is it called a Winbridge oscillator? If you look at this circuit, and call this point as A and this point as B, then you can redraw this circuit in the following manner. You can redraw it in the form of a bridge. R1 and R2. R2 is grounded and this point is A. Then from the end of R1, that is the output of the op-amp, goes a series combination of C and R, and this combination goes to ground through the parallel combination of C and R, and this point is B, let us say. This is my output voltage V0. Okay, in between A and B you have the inverting and the non-inverting terminal of the op-amp, and you see that this exactly looks like a bridge. It was first introduced by the German gentleman Wien, and therefore it is called a Winbridge. It is used for measuring the unknown capacitance and its leakage. This bridge is used for measuring a capacitance and its leakage. Usually the unknown capacitor is put here, and these two are made variable. Obviously you cannot make them equal, so let us say this is C2 and alright CB and RB and let us say this is CA and RA. You can find out the conditions under which the bridge would be balanced. Okay, the condition would be R1 by R2 should be equal to RA plus 1 over j omega CA divided by RB divided by 1 plus j omega CB RB. And if you clear the fractions, you can find out the relationship that is needed for balance of bridge. Two conditions would be there, one for imaginary parts on both sides being equal and one for real parts being equal. Okay, two conditions are needed which will give the two unknowns, namely CB, the unknown capacitance, and its leakage, which is represented by a shunt resistance R sub B. In the present case, if you find the condition for balance of the bridge, you will see that R1 by R2 is equal to R plus 1 over j omega C divided by R by 1 plus j omega CR, and if you clear this, you will see exactly what we got for the condition of oscillation, namely you get a balance at the frequency omega 0 equal to 1 by CR, and R1 by R2 has to be exactly equal to 2.
So where's the CA and R?
Oh, in the present circumstances, CA equal to CB equal to C, and RA equal to RB equal to R. I was going back to the oscillator condition, but in general CA, RA, CB, RB. Okay. Now that is the story with regard to a Winbridge oscillator. Now with regard to this oscillator, it is very easy to see how one stabilizes the amplitude. As I mentioned to you earlier, the gain, if it is exactly 3, then oscillation may or may not start. It may be a squegged oscillator. I don't know if you have got this term in the dictionary, squegging. That means it oscillates for a short time, then goes off. Then again comes for a short time, goes off, and these are uncertain. This is called squegging. That means an oscillator is willing to oscillate, but unfortunately as soon as it starts oscillating, something goes wrong, it stops. This is called squegging. Now in order to stop this, what one does is the gain is made slightly greater than 3 plus delta, and a practical arrangement would look like this. Let me show you the arrangement, then I will explain. A practical arrangement okay, let's go back to this minus plus. I will not draw the RC circuit. I'll draw only the amplifier. What modifications are required in the amplifier? What is done is, let's say this is twice R prime, which goes here. This is R1. R2 should be equal to R prime, right? But it's made 0.8. 0.8 and then it goes to ground through another resistance which is 0.15 R prime. It is broken up into two parts. This is a practical circuit. The rule of thumb, I mean there is nothing strict about it, but this circuit works. If you find the gain is 1 plus 2 by 0.95. So it is slightly greater than 1 and the gain happens to be 1.04, slightly greater than 1. Okay. So the oscillation starts. Yeah, the gain is 3.04, that is right. The gain is 3.04 greater than 3 and the oscillation starts. Now how does it stabilize? Normally if you do not take any precaution for stabilizing the amplitude, what happens is the amplitude goes on increasing and obviously it will give a distorted waveform, it will not give pure sine wave. But one can do something, one can use this instead of a fixed resistance, one can use a resistance with a positive temperature coefficient. Positive temperature, that means if the temperature increases, the resistance increases. Okay. Now you know the gain is 1 plus R1 divided by R2. Suppose due to some reason, please follow this, suppose due to some reason the output voltage increases. Suppose it increases, then what happens? Output voltage is voltage between this point and this point, and therefore the voltage across 0.8 R prime also increases. If the voltage increases, current increases, so this resistance gets heated and this heat causes the resistance to increase and therefore the gain shall decrease. Thus this is the stabilizing effect. On the other hand, if you do not want to use a PTC is not available, an NTC is available, then put that NTC here. Same effect. If V0 wants to increase, this will cause V0 to decrease. Okay. So temperature sensitive resistor is required for stabilizing amplitude. In the olden days, when NTCs and PTCs were not readily available, people used to use an ordinary bulb, light bulb, in place of one of these resistors. Of course, op-amps were not available, they used to make with valves, and therefore valves, VALVES, and therefore BULBES were the natural choices. And obviously electric bulbs are temperature sensitive. Positive or negative? They are positive temperature coefficient. Okay. One of the commercial Winbridge oscillators does not rely on this only, it uses in addition two Zener diodes in parallel with these two. That is, one of them is like this, a very interesting concept. Let us see, should I draw like this? No, it should be like this. These are two Zener diodes, identical, with a voltage, with a Zener breakdown at Vz, okay, with a Zener breakdown at Vz. Now normally, because the gain is 3.04, which is greater than 3, oscillations start. And since the gain is greater than 3, oscillations build up. When the oscillations build up, both the Zeners are non-conducting, they do not conduct, till the amplitude of oscillation rises to Vz, not exactly Vz, Vz plus 0.7, agreed, Vz plus 0.7, because if this is positive, let us say, if this is positive and this is negative, then this conducts in the Zener region and this diode conducts in the normal region, okay. And therefore, as soon as the amplitude of oscillations exceeds Vz by a small amount, VBE on, well, the Zener stabilizes the amplitude. it does not allow to go beyond that, alright. Similarly in the negative direction, and therefore the amplitude of oscillation gets cut off at Vc, approximately Vc. Okay. If this Vc is 6 volt, then the amplitude of oscillation stabilizes at 6 volt. Is the point clear? If the amplitude wishes to go down, then this becomes non-conducting, again this takes over and it builds up the amplitude to Vc. Okay. The voltage across these 2 points, the amplitude cannot exceed Vz plus Vbe on, because the diode cannot support more than this. So it is a case of the so called AGC, automatic gain control of the device. Okay, as I had mentioned earlier, these RC oscillators are useful only up to 100 kilohertz or so. If you go beyond that, then it is more convenient to use LC oscillators, LC, and the general configuration is the following. General configuration for an LC oscillator is the following. What you require is a inverting amplifier. An inverting amplifier which is ideal in all respects, except that it is allowed to have a non-zero output resistance R0. Okay. This is the non-ideality that we can permit. Of course, we will permit later a finite input resistance also, but to see how things work, we have a inverting amplifier of gain mu and output resistance R0, so that if this voltage is Vi, then the output shall be modeled as mu Vi with opposite polarity in series with R0. Okay. This is the model that will permit of this device. It could be an op amp. If it is op amp, then R0 obviously would be approximately 0. If it is not, if it could be a FET, it could be an FET, then the output resistance is approximately capital R subscript capital D, but the input is approximately infinity. Okay. Then this goes to a passive network like this, 3 impedances Z3, then Z2 and Z1. It goes to 3 impedances and this point is connected together. The middle point is grounded, okay, and this is fed back to the input. This is the general configuration of a simple LC oscillator, okay, where Z1, Z2, Z3 are either inductances or capacitances. And in the analysis, we will assume all the 3 to be ideal reactances. That means Z1 is JX1, where X1 positive means Z1 is an inductance. Z2 is JX2. If X2 is negative, it means it's a capacitance. Similarly, Z3 is also JX3. Although you know that you cannot make an inductance or a capacitance without a resistance, we will first ignore the resistance, the non-ideality. Now, obviously, the A and beta are not very difficult to find out. What would be A, for example? For A, you have minus Vi R0, and here there would be an impedance Z. This is V0, okay, the A circuit, and this impedance would be Z2 in parallel with Z1 plus Z3. Is that okay? No? Let me draw it again. It's okay? Alright. The equivalent circuit is mu Vi minus plus R0. Then we have 2 ground is Z2. Okay? 2 ground is Z2. And then we have Z3 and Z1. The other end of Z1 is also grounded. and this is my V0. Okay, so this is the A network, and therefore the gain A would be equal to minus mu, the gain I am finding with respect to Vi. Okay, V0 by Vi, this is the basic amplifier. I have opened the loop. Okay, so minus mu divided by, multiplied by the load, which is Z2 Z3 plus Z1 divided by Z2 plus Z3 plus Z1, agreed, divided by R0 plus the parallel combination of Z2 and Z1 plus Z3, Z3 plus Z1 divided by Z2 plus Z3 plus Z1. This is my A. I can also identify beta very simply. From the output voltage, a fraction from here is taken and fed back to Vi, to the input, and therefore beta is simply equal to Z1 divided by Z1 plus Z3. Agree? I have identified A, I have identified beta. All that is required now is to multiply the two and put equal to 1. Agreed? Let us do that. If I do that, then I get, after a little algebra, I get minus mu Z1 Z2 divided by R naught Z1 plus Z2 plus Z3 plus Z2 Z3 plus Z1. You can see this very easily how this simplification is done. This has to be equal to 1. This is the condition for oscillation or the Barkhausen criterion, A beta equal to 1. Now we substitute the condition that all these elements Z1, Z2 and Z3 are reactive. So Z1 is Jx1, Z2 is Jx2 and Z3 is equal to Jx3. If I substitute this, then I get in the numerator I get mu x1 x2. Is that clear why the negative sign disappears? Because x1 is, Z1 is Jx1, Z2 is Jx2, J multiplied by J is minus 1 divided by J R0 x1 plus x2 plus x3. What do I get here? Minus x2 x1 plus x3. Alright, this has to be equal to 1. The right hand side, in the right hand side the angle is 0 degree, so the left hand side angle must also be 0, and one of the essential conditions is that the imaginary part should vanish, which can vanish due to two reasons. Either R0 is 0, which we have not assumed, and the other reason is x1 plus x2 plus x3 should be equal to 0. So my essential condition is that x1 plus x2 plus x3 equal to 0, which can happen only if at least one of the elements is of a different sign. Isn't that right? At least one of the elements. Okay. What do you mean at least? Only one can be of opposite sign because there are only 3 elements. So 2 inductances, 1 capacitance, or 2 capacitances, 1 inductance. Alright. If this is true, then obviously x1 plus x3 should be equal to minus x2. If this is true, now if I substitute back mu x1 x2 divided by, the reactant term is 0, the imaginary term is 0, so minus x2 multiplied by x1 plus x3, which is also minus x2. Therefore this should be equal to 1, which means that mu should be equal to x2 by x1. Alright. So these are the conditions of oscillation. One is that this should be satisfied. This is the first condition and this is the second condition. That is, the reactive element should be so chosen that their sum is equal to 0, and the gain of the amplifier should be x2 by x1. It does not depend on x3. x3 therefore determines the frequency of oscillation, and x1 and x2 determine the condition for oscillation. and you of course know that mu has to be slightly greater than this. Okay, the condition of oscillation therefore. Now can x1 and x2 be of opposite signs? No, because by definition mu has been assumed to be positive. We took minus mu vi. Okay, so the condition of oscillation is that x1 2 same sign, that is both are either inductors or both are capacitances. x3 of opposite sign and mu should be equal to x2 by x1. These are the conditions of oscillations. Accordingly we can have two different types of oscillations. For example, x1 and x2, suppose both are inductances L, then x3 should be a capacitance. Agree? Let us look at this circuit. Minus, plus, this is grounded, this is the input, this is mu R0. Now x3 is a capacitor, so I have a capacitor here C. Then I have two inductors. Was this x2 or x1? This was 2. Okay, so this is L2 and this is L1, and then you have this point is grounded and this goes to the input. Okay, mu now has to be L2 by L1. And what is the frequency of oscillation? The sum of the three reactances should be equal to 0, which means that the three reactances should resonate in series resonance. So what is omega 0 then? 1 over square root C L1 plus L2. Very good. No further analysis is needed, absolutely by inspection. This it goes by the name of Hartley oscillator. Hartley is the name of a British gentleman. I don't remember his initials. Hartley oscillator. Hartley oscillator is the one in which two inductors are used and one capacitor. As we shall see a little later, this is a little unfavored as compared to the other possibility. That means two capacitors and one inductor. If x1 and x2 are both capacitors and x3 is an inductor, then the circuit becomes like this. Mu R0, we have an inductor here, then two capacitors, this is C2 and this is C1, the middle point is grounded, these are connected, that's how it goes. Okay, now what would be the required mu? No. C1 by C2, because the reactance is 1 by omega C. Okay, and what would be omega 0? Obviously 1 by square root of L, not C1 plus C2, but C1 C2 divided by C1 plus C2. That's right. Okay, everything by inspection. Now this will work perfectly all right, provided you get a device like this. Suppose mu R0, the worst thing that can happen is that you use a single BJT, a BJT, bipolar junction transistor. Then you have a finite input impedance, also a non-zero output impedance. Okay, let's see what can happen. Let's have a single BJT, the usual methods of biasing, plus VCC. Then you have the two resistors here, R1 and R2. This is your input point, and suppose it's a I beg your pardon, I didn't mention this. This is called a Colpitts oscillator. Colpitts is also the name of a person. Colpitts oscillator. One is two inductor is Hartley and 2 capacitor is Colpitts. I must go back and tell you why Hartley is slightly unfavored as compared to Colpitts. Can anyone guess the reason? Hartley is not preferable as compared to Colpitts. If you have a choice, you go for Colpitts. Why? Inductors are difficult to make. Suppose, as I said, at 1 megahertz, inductors are not difficult to make. You give me a short length of wire and this pen, I will make you a good inductor. But there are other problems. If you have 2 inductors, they couple with each other. There is a mutual inductance. Not only that, any other circuit element nearby will also get coupled. And therefore the whole circuit becomes an electromagnetic interference, an island of electromagnetic interference. Okay. Nevertheless, these are done. One of the inductors or both the inductors have to be shielded, and very simple shields work. Just raise an aluminium partition between the two. You just have to break the magnetic lines, that's all. Okay, simple shields do. Of course, in the market, sophisticated shielded inductors are also available. You can ask, if it is shielded and sealed, how do you change the inductance? Well, there is a screw at the top which varies the length of insertion of a ferrite rod, the core inside. If it goes further inside, inductance increases. If it comes out, inductance decreases. So variable inductors, very high quality inductors are available in the market, provided the frequency is high, of the order of a megahertz or so. Okay, so on the other hand, in the Colpitts oscillator, capacitances can be made without much of electrostatic coupling between them. Okay, without much of electrostatic coupling between them. Now suppose you want to make a Colpitts oscillator with a single BJT, then obviously the beta circuit would be like this. You will have a capacitor here. Which capacitor is this? C2 or C1? C2. Then you have the inductor, and then you have a C1 which goes to ground, and this has to come to the input. Obviously, you can't bring it like this, you must bring it through another capacitor, a blocking capacitor, which has to be very high compared to C1 or C2. Agree? Number 2, can this be coupled directly? Oh, there are problems. Even though there is a blocking capacitor here, see, there is an inductor here. No, you answer my question. Can this be coupled directly from here to here? Will DC go? Yes or no? There is a capacitor here. How can DC go? Through the inductor, it cannot flow through the capacitors to ground. If it is, that's okay, but there is a DC here. There is a DC voltage VCE here, okay, which will appear across this capacitance. No problem. The inductor cannot pass DC because of this capacitor. So this is a good circuit. In a practical circuit, we don't want to unnecessarily waste power, and this is not an absolute need, this resistance. Why was this resistance needed? To bias the transistor and also to provide the required, at what frequency? At the frequency of oscillation. Isn't that right? So what one does is, instead of using a resistance, one uses an AC load, which means you replace this by means of an inductance, a high valued inductance, because you require a gain of, ideally the gain required would have been 3, but what one does is one uses a high valued inductance so that there is no DC dissipation in this, and high value can be obtained only by putting a core. So this is called an RF choke. RF choke. What does an RF choke do? It chokes RF. As simple as that. In other words, it does not allow RF to pass through this. Where should RF go then? It must go through the feedback circuit. Is the point clear? Okay. Instead of this resistance, one uses an RF choke, a high valued inductance. Okay. Now, if I draw the equivalent circuit, this can of course be taken as short, but R1 parallel R2 parallel R pi, that is what will come, and therefore if you open the loop, you have C2 L C1, then it should be terminated in R1 parallel R2 parallel R pi. Okay. Now what comes here? Here comes the RF choke for all practical purposes can be taken as of infinite impedance as compared to the impedance offered here. Okay, and therefore that we can ignore. We have a current generator GM V pi in parallel with R naught. This is what gives the output impedance, and you see the output impedance is far from being negligible. Agreed? But as you know, the output impedance does not affect the condition for oscillation, neither does it affect the gain requirement. The gain requirement is simply C1 by C2, it is not affected by R0. All right, then you have GMV pi and this is Vi, this is R pi, this is V pi. Okay, this is the total circuit after opening the loop, and in order to find out the condition for oscillation now, obviously the oscillation frequency as well as the required GM shall now be affected by R0 as well as R1 parallel R2 parallel R pi, and you will have to find this out. Is the position of L okay? Yes, it is okay. It lies between the two capacitors.
But the direction of current is on the,
Oh, I have made a mistake. Otherwise it would not work because we wanted an inverting amplifier. This is the equivalent circuit of the transistor. Okay. So what I am mentioning is that if it is a BJT, then you shall have to be careful. You have to analyze this circuit. Now, what is the condition for oscillation now? That this voltage should also be equal to V. So you forget about this part. You start from here, find out this voltage, and equate that to V pi. That would give you the condition for oscillation. And this is the general philosophy of analysis of such circuits. If you had, instead of the RF choke is the thing that is used in, you open any radio frequency circuit, even in amplifiers they use RF choke instead of a resistance. And the purpose is that you reduce the requirement of power supply because there is no DC drop in the RF choke, and you reduce the dissipation. So in high power circuits, for example, the modulator amplifier in a transmitting station, 50 kilowatt transmitting station, and you can understand the amount of dissipation that one has to go. Even a few kilowatts of dissipation saving makes a lot of saving in transmission. So one uses usually an RF choke. These LC oscillators, unfortunately, are not very stable oscillators. They are not very stable because of various reasons. You use inductors. If the inductor picks up a certain magnetic field from a nearby circuit, the frequency strays, frequency goes stray, frequency deviates from what the value should be. If the temperature changes, the inductor, the capacitors, the resistors, all of them will change, and therefore the frequency deviates. There is a particular circuit which is obtained with a solid state material, a crystal, which is equivalent to either an inductance or a capacitance whose value remains very stable irrespective of changes in the external circuit. And the material that is used for the crystal is either quartz, QUARTZ, or zinc oxide is one of the materials, or lithium niobate, NbO3. I am not too good in chemistry. Lithium niobate. These are the materials. Also aluminium nitride, ALN, aluminium nitride or nitrate, I don't know. IDE? Okay, aluminium nitride. These are the materials from which a crystal is made. And if you know what a crystal can be cut in various symmetries. And the usual symmetries that are useful for oscillators are either AT or BT cut, AT or BT. Just remember the names. We don't want to go into the physics of this cut of the crystals, but the phenomenon that is utilized is called the piezo electric effect, PIEZO electric effect. And this effect is as simple as this. If you have a block, let's say a rectangular block of the crystal which is properly cut, and suppose you apply mechanical pressure to two of these faces, okay, suppose you apply mechanical pressure, you take a box, apply mechanical pressure, then it turns out that the opposite, the other two faces, the other perpendicular faces develop a voltage, an electric voltage. The material itself is non-conducting, it's an insulator, it's a dielectric material, and you can understand why it happens. The physics is that there is a polarization of charge, that is, positive charges go on one side and negative charges go on the other side. Well, the charges are not mobile. How come they move? What happens is, take a dielectric molecule, it contains positive as well as negative charges, so these molecules orient themselves so that the positive face is, let's say, up and the negative face is down. So there appears a charge on this surface and a charge on this surface. This charge is not mobile, it's an electrostatic charge. Yeah.
Then how can these piezoelectric crystals provide current?
Oh, I'm coming to that. I'm coming to that. Now, on the other hand, if you provide an electric field, that is, if you connect a potential difference between the two, the effect is reversible. That is, there is a mechanical deformation. All right. So, if this, instead of a DC, if it is AC, then the mechanical deformation, there is a compression and expansion, compression and expansion. If this is AC, okay, so if the direction of the field changes, compression changes to expansion. All right, and if yes,
So this happens to 4 faces.
this happens to,
All the 4 faces, remaining faces.
I have taken all the 4 faces. Oh, the remaining ones.
Yes.
No, these are the. It happens on the other faces also. But you have to cut the crystal in such a fashion that the effect is dominant on 2 of the faces only. This is why AT and BT cut crystal. Okay. Now the basic phenomenon is this, that if this is an AC, then the mechanical deformation, it expands and contracts alternately in consonance with the AC. Okay. Now if the frequency of this AC changes, if it is kept varying, then obviously the mechanical vibrations will resonate at a particular frequency. Okay, and this is what is utilized in a crystal in an oscillator. That is, you apply a field which is by the oscillations, which produces mechanical resonance. If it produces mechanical resonance, and if Barkhausen criterion is satisfied, then the oscillations are self-sustaining. Okay, oscillations are self-sustaining. However, you cannot observe this you cannot observe this mechanical resonance on with naked eyes. The crystal itself is very small, typically 1 centimeter, 1 centimeter, 10 millimeter. This is a typical dimension. And obviously, in order to apply a field, because this is a dielectric, you have to have two faces coated with metal from which you take the terminals. And if you do that, obviously you create a capacitance. A dielectric material between two metal plates is a parallel plate capacitor. And therefore, the equivalent circuit would be that you have a capacitance between the two metal plates, and the bulk itself has mechanical resonance at a particular frequency. So, in parallel, the effective equivalent electric circuit would be a series resonance circuit, L and C. But unfortunately, there is some dissipation also, and therefore you have a resistance. This describes the equivalent circuit of a crystal, a capacitance shunted by a series resonant RLC circuit. This R is a very small quantity, and in the analysis, as you will see next time, we shall ignore this R and carry out the analysis. We will continue this tomorrow.